Hello, welcome to a new module of derivatives. Today we are going to review the L'Hopital rule, and we are going to see examples of limits solved with this method. The requirements are very few: to know a little bit the concept of limit and a little bit of basic mathematical symbology. The L'Hopital's rule can be summarized as follows. Consider two functions, f of x and g of x, both of which are differentiable at a point x equal to a. So that the derivative function g, and substituting the x for a, it is different from 0. That is, g prime is different from 0. And so that the limit of the function f of x and the limit of the function g of x when x tends to a, both limits are 0, well then the following is true. The limit when x tends to a of the quotient between f of x and g of x is the same as the limit when x tends to a of the quotient between its derivative between f prime of x and g prime of x. Let's briefly discuss this category of limits. Under the conditions specified by the L'Hopital's rule, as outlined above, when the limit of f of x approaches 0 and the limit of g of x also approaches 0, as x tends to a, the following holds true. The limit of the quotient results in an indeterminate form, specifically 0 over 0. In such cases, we typically refer to this as a type of indeterminacy known as 0 over 0. This doesn't imply that the limit is non-existent or impossible to compute. Rather, it indicates that we need to put in some additional effort to determine the accurate limit of this quotient. In this case, we'll introduce a concise rule that will help us determine the limit of the quotient f of x over g of x when it results in the indeterminate form 0 over 0. Let's explore an easy example. The limit as x approaches 0 of sine of x over x. To begin our analysis in this case, if we attempt to calculate the limit directly, we can take the limit as x approaches 0 for sine of x over x and substitute x with 0. Let's examine the outcome in this case. The sine function, if we substitute x with 0, we have sine of 0 over 0, which presents a challenge due to the denominator being 0. When x is 0, sine of 0 is, as you recall, equal to 0. Consequently, we end up with 0 over 0, which is a situation of the indeterminate form 0 over 0. What's the solution? Let's apply the L'Hopital's rule to resolve this indeterminacy. The straightforward approach here is to differentiate the numerator and denominator individually. To clarify, this doesn't involve applying the derivative of a quotient rule, where we differentiate the numerator and multiply by the derivative of the denominator minus the derivative of the numerator times the denominator squared. Instead, in this case, the L'Hopital's rule simply entails differentiating sine, which becomes cosine in the numerator, and differentiating x, which yields its derivative, which is 1. We've determined that this limit is equal to this new limit. Let's explore if this new limit provides us with any information. When attempting to evaluate this new limit, the initial step is to replace x with 0 in the quotient. This results in cosine of 0 over 1, which simplifies to 1 over 1 because cosine of 0 equals 1. Please keep that in mind. So we find that the limit as x approaches 0 of sine of x over x equals 1. We've essentially taken the original limit, which initially gave us 0 over 0, differentiated the numerator and denominator, and re-evaluated the limit, which now yields a result of 1. Therefore, the limit we aim to calculate is 1. Let's see the graph of this function. One crucial point to bear in mind is that the sine function of x over x, apart from the limit discussion, lacks a clear definition when x equals 0. Upon substituting x with 0, no specific value emerges, yet the limit can still be calculated. Now let's turn our attention to the graph of this function. As x steadily approaches 0 from the right, the function converges towards the value 1 from the right side. Likewise, when x approaches 0 from the left, the function also tends to 1 from the left side. This signifies the existence of a gap where the function remains undefined. However, on both sides of this undefined point, it steadily converges towards the value of 1. In simpler terms, it constitutes an avoidable discontinuity in the function with a minor gap that temporarily disrupts the function's continuity. Now let's examine another example. I recall that this particular example was featured in the June 2014 selective exam for Mathematics 2. If I'm not mistaken, it was part of an exercise that required analyzing the continuity of a piecewise defined function with one segment of the function involving the same quotient we've been discussing. When you're tasked with calculating the limit as x approaches 0, a challenge arises. If I try to calculate it in a direct way, what I get is, substituting all x with 0, we end up with 0 plus 1 times sine of 0 over 0. We basically replace x with 0 in the expression. What we observe is an indeterminate form, 0 over 0, which requires the application of a particular method to determine the limit. Which rule are we using in this case? The L'Hopital's rule. We will attempt to apply this very rule to the expression. Initially, we have the limit, and I apologize for the omission of x plus 1 here. It should read as x plus 1 times sine of x over x. Even though the derivative is already present, I will endeavor to derive it in relation to the numerator above. What do we have to do? When applying L'Hopital's rule, we start with differentiating the numerator. Let's take a closer look at the numerator. It's a product, so we apply the product rule, which is straightforward. The product rule involves the derivative of the first term, which is 1, multiplied by the second term sine of x, plus the first term without differentiating, multiplied by the derivative of the second term, which is cosine of x. Now we differentiate the denominator separately, and the derivative of x is simply 1. In this case, does this limit provide more information than the previous one? I believe it does. If we replace x with 0 in this case and calculate the limit, we find that there is no indeterminate form. Substituting x with 0 results in a limit of 1 over 1. The cosine of 0 is 1, and 1 multiplied by 1 is 1, while the sine of 0 is 0. Therefore, the limit of this function is 1. Regarding its graph or graphical representation, take a look at what the graph of this function looks like. Whether I approach it from the right or from the left, the function converges to 1 from both directions. It's important to note that the function is undefined at x equals 0. Now for our final example, we'll calculate the limit as x approaches 0 of cosine of x minus 1 divided by x squared. This example is interesting as it involves two chained L'Hopital's rules. Given that we've previously established the limit of sine of x over x as equal to 1, let's see what is the outcome of this exercise. To begin with, we should attempt to calculate this limit directly. What's the limit as x approaches 0 of cosine of x minus 1 divided by x squared? It's quite straightforward. I substitute x with 0, and the result is 1 minus cosine. I apologize for the mistake. It's actually the cosine of 0 minus 1 over 0, which gives us 0 over 0. The point to note is that we have an indeterminate form of 0 over 0. Can we use L'Hopital's rule in this case? Absolutely, we can apply it. What's our subsequent course of action, you may wonder? Our next step involves taking the original limit and differentiating both the numerator and denominator separately. We find the cosine of x minus 1 in the numerator, which yields a derivative of minus sine of x. In the denominator, we have the simple x squared, which upon differentiation gives us 2x. Now, after factoring out the minus 1 and 2, this limit simplifies to sine of x over x as x approaches 0, which we've seen in the first example. There we found that the limit of sine of x over x as x tends to 0 equals 1. Therefore, the limit of this expression is minus 1/2. If you're uncertain about this limit, I encourage you to apply L'Hopital's rule once more to verify that it indeed equals minus 1/2. Therefore, the limit of this function, cosine of x minus 1 divided by x squared, is equal to minus 1/2. Regarding the graph of this function, it's important to note that the function is not defined at x equals 0. However, as you can observe on both the left and the right, the function approaches the value of minus 1/2, which aligns with the limit we calculated. I'd like to highlight some important notes regarding L'Hopital's rule. First, it's crucial to apply this rule exclusively when dealing with indeterminate forms of the type 0 over 0. There are various other types of indeterminate forms. We'll explore one of them in point 4, which will also provide a small note to broaden its applicability. In principle, it's primarily used to resolve indeterminate forms of the type 0 over 0. Second, it's worth noting that L'Hopital's rule may not always make the task of calculating a limit simpler. Allow me to illustrate this with an example. Imagine I ask you to determine the limit as x approaches infinity of e raised to the power of minus x divided by 1 over x. To evaluate this as x approaches infinity, we need some additional information. But I believe you can grasp it. E raised to the negative infinity equals 0, which is a crucial fact you should be aware of. Additionally, 1 divided by infinity equals 0. Therefore, when we evaluate this limit as x approaches infinity, we obtain an indeterminate form of 0 divided by 0. If you apply L'Hopital's rule in this scenario, you will actually make the situation more complex. You can try it as an exercise to see for yourself. Point 3. It's essential to recognize that not all limits of the form 0 divided by 0 can be resolved using L'Hopital's rule. It's possible for the limit of f of x over g of x to exist, while the limits of their derivatives do not exist. Lastly, Point 4. L'Hopital's rule can also be applied with minor adjustments to resolve indeterminate forms of infinity over infinity, hence expanding its applicability for addressing limit problems. I trust that this information has been or will prove to be valuable for you. We've covered L'Hopital's rule and explored 3 illustrative examples of its application. Thank you very much for your attention and see you soon.